Okay, we've made it to part 3 of energy grade lines and hydraulic grade lines. And in this case, we're going to look at the situation involving a flow with a real fluid that has losses, energy losses. And there's really two types of losses that we're going to see in this system. As flow first enters the pipeline, there's going to be a little localized turbulence. And so we're going to have something here called a minor energy loss. And it's going to be a small loss of energy that's localized right here where the flow enters the pipeline. Then, as the flow continues through the pipeline, friction is going to slowly take out energy from the system. Basically, it's a gradual reduction in the energy based on the friction of fluid with the pipeline. So based on that sort of qualitative description, I can write how or draw how the energy changes with distance based on the updated energy grade line. So what I'll do is, since there's going to be a little bit of an energy loss right here, I'm going to draw a small dip in my energy grade line right at the beginning. And then and that's going to count for the minor loss. And the next thing I'm going to do is I'm going to draw a sloping line all the way to the outlet, and that will account for the losses due to friction. So now I'm going to draw the sloping line like that, okay? So the slope represents the rate at which friction is taking energy out of the flow, and this distance right here represents the energy lost right at the inlet, something we call a minor loss. So if I label my energy grade line, what it tells me is that in this system I have, at the beginning of the system, energy proportional to the height of the tank, which is labeled here ZA. And when the flow enters the pipeline, you lose a little bit of energy with some localized turbulence that dissipates energy. And then the process of pushing fluid through that pipeline leads to energy losses, because flow, as it touches the sides, there's some friction there basically, and that dissipates some heat, and you have loss of energy. So the energy grade line goes straight down. The reason it's straight is that the pipeline it's a uniform material. We're going to assume it's, say, all steel or iron or PVC or some uniform material property. And also the diameter of the pipeline, we assume, is uniform, so the diameter stays the same. And because of that, if the diameter is staying the same, that means the velocity in the pipeline is the same here and here and here and here. So there's no change in velocity of the pipeline with respect to x. When all those things are the same, the rate of friction also stays the same. And so if the rate of friction is the same, then the energy is lowered at a uniform rate, and you get a straight line for an energy grade line. So now we need to draw the hydraulic grade line. And to do that, it's helpful to start down at the other end and note that here at point C, we have some pressure with C over gamma plus Vc squared over 2g plus the elevation at C. And since this jet of fluid is exposed to the atmosphere, the pressure here is just an atmospheric pressure, so that goes away. There is some velocity still in that jet, so that doesn't go away. And then the height here is ZC, and that's represented by that height. So what that means is that when the flow finally makes its way out to the end, this distance here, since the pressure is 0, this distance represents V squared over 2g. So that distance is what we call the kinetic energy head. And that distance will be the distance between the energy grade line and the hydraulic grade line. So you notice that the hydraulic grade line is P over gamma plus C. The energy grade line is P over gamma plus C plus V squared over 2g. So the difference between the EGL and the HGL is always V squared over 2g. So that means that the HGL will always be underneath the EGL by an amount equal to v squared over 2g. So I'm going to draw that here. It's going to start in the center of the pipeline. It's going to be parallel. Okay. So this is the hydraulic rate line. This distance is v squared over 2g. And this distance here, which is the distance from the hydraulic grade line to the center line of the pipe, that just represents P over gamma. So this distance here is P over gamma. So what's happening in the system, we have a tank of liquid. All the energy is in the height. As soon as the flow goes into this pipeline, you lose a little bit of total energy. And then a lot of the energy goes into kinetic energy. So this big distance here represents the kinetic energy. There's just enough energy left over to maintain some positive pressure here. So that's P over gamma. And then this distance here represents Z. So at any given location along a pipeline, one of the distances, the distance from your datum up to the pipeline represents the height Z. The distance from the pipeline to the HGL represents P over gamma. And the distance from the HGL to the EGL represents E squared over 2G. So this shows you why EGLs and HGLs are a graphical tool used by civil and environmental engineers to analyze pipelines. It's useful. You can see as you go along here, you can see how the pressure in the pipeline is going to be reduced. And so if you had some standards, you want to achieve a certain pressure in your pipeline, you can immediately see where the pressure is going to be low and where you might want to add a pump or something to do something about that. So this is your third example of an EGL and an HGL, and we're going to do more in class.